Mac here. Today we're going to be looking at parts of circles. So a circle is a figure consisting of all points in a plane that are given at a fixed distance called the radius from a given point called the center. Very often we use to describe the circle, we say circle A, and we could use the circle symbol, which is a circle with a dot in the middle, circle A, and it has a radius of AB, or segment AB is the radius. So what is a radius? The distance from the center of the circle to any point on the circle's circumference. We usually use little r to denote the radius. You know these first two, but what is a chord? A chord is a segment that joins two endpoints on the circumference of the circle. So let's get another point here. How about if I have point C join and I make segment CB. Segment CB is a chord. And our radius here was, let's go ahead and put a line here for AB. And this was our radius. Use capital letters for points. Very good. Okay, so that is chord CB, and notice the chord is always going to be inside the circle. So this is our chord right here. Okay, diameter. It is a segment that passes through a circle center with endpoints on the circumference of the circle. So how about we go from point C, passes through the center at point A, and ends at point D. CD is our diameter. And we also know the relationship that the radius equals 1/2 of our diameter D. And we use little d usually to denote diameter. Okay, secant. A secant is a line that intersects the circle in exactly 2 points. We'll do this. And we'll call this point EF. So line EF is a secant. So capital E, capital F, use my line symbol. And so it passes through the circle in 2 points, and a line extends infinitely in both directions. So that's a secant. So a chord has 2 endpoints, is inside the circle, and the points are on the circumference. Secant has points on the circumference too, but it's a line that extends infinitely. Okay, tangent. So tangent is a line that intersects a circle or a curve at exactly 1 point. Let's go through right here. So I'm going to make a line here, and this line intersects circle A only at point B. And maybe I'll put another segment or point over here and call this G. So BG right here, line BG, is a tangent. It's tangent to circle A. And this is only true if it only has 1 point on the intersection of the circle. If it had 2 points, it would be called a secant. Now there's a special property here of tangents, and that is tangent to a circle is going to be perpendicular to the radius. So tangent lines are perpendicular to the radius. Right? right? So tangents are perpendicular. Perpendicular to the radius. Yeah, so, therefore, AB, segment AB is perpendicular to line BG. Okay, so the point of tangency is the point at which a tangent intersects a circle. So right here, that is the point of tangency. And the tangent is always perpendicular to the radius drawn to the point of tangency. Kind of already covered that. Alright, so this point B right here is the point of tangency. Could have really rolled this into one definition, but oh well. Point of tangency. Very good. With three more here, we have tangent circles, concentric circles, and congruent circles. Circles that intersect at exactly one point. Those are tangent circles. Let's pop that on there. I think I gotta go up. Keep going up. Yep, there it is. Alright, circles that intersect at exactly one point. How about we get let's get an example here what that looks like. Okay, so two circles here. Let's call this circle A and B. And let's put B up here. And they both share, they intersect at exactly one point. We'll call that C. And from the point of tangency, we would be able to draw a tangent line like this. So this tangent line is tangent to both circle A and circle B. Yeah, so therefore, when I draw the radius here from B to C, this is going to be a right angle. And when I draw the radius from A to C, this is also a right angle. And what it really tells us is that points A, B, and C are all going to be collinear, right? And this, when we have this situation, A, B, and C are collinear. And that means they lie on the same line. B is going to be, I'm going to put a point D here, so that means that segment AB is perpendicular to line CD, right? Two or more circles that have the same center but different radii. Radii is just the plural of radius. I don't say radiuses. Here we see some concentric circles, right? So they all have the same center, but they all have different radii here. And how about, right, so they have different radii, same center. All have the same center right there. Okay, congruent circles. So congruent circles have the same radius, And congruent figures have the same size and shape. So these circles are all going to have the same size and shape. So I can do it this way. So circle here, circle here. Let's try that one again. Like that. And one way we can denote congruent radii, let's say we've got we have circles A, circles B, and circles C. I say, well, these segments are congruent. Those are the radii. So these circles are all also going to be congruent. So circle A is congruent to circle B is congruent to circle C. Okay, we have all of our definitions for this section, as well as some figures. Let's take a look at some examples, at example 1 through 5 here. And 1, we're just going to select the parts of circle A that best fit the description, right? Okay, so there's a couple of possible examples for many of these, potentially. So we're looking for a radius here for number A. So what do we have for radius? We could say AF, segment AF, segment AH, segment AG, AD, AC. Let's just go with AF. So we have segment, I don't know, what happened to my size here? That's interesting. Got small on me. Let's get my brushes out. A little bit bigger. There we go. Okay, so we've got, how about segment AF? A chord. Okay, so chord has 2 endpoints on the circle. So I've got, this is a good one right here, segment DG. By the way, is a diameter a chord? Yes. So we can also use the diameter here, which is HF, right? So HF is also a chord. We could also, I mean, we see this as a line here, CD, but we can also just pick out the segment out of it. We can just say segment CD. That's a chord. Okay, just the part that goes between the 2 endpoints. That's acceptable. And there are other ones. Let's keep going. A tangent line. Well, it appears that HJ is a tangent. Let's go ahead and add a symbol here. Let's say that this is perpendicular, and if this point is on, H is on the circle, then we know that this would be tangent, right? So it'd be nice to know that little piece of information. And let's put that, so a tangent line, we've got HJ. So H, line HJ, put our symbols. Of course, we could also say HB or JB is another way of saying that line. I don't see any other ones that are tangent. Point of tangency, well, that's going to be that point right there, H. So we can just say capital H, or if we want to write point H. Diameter, we already said, is HF. Segment HF is our diameter. And the secant is a line with two intersections on our circle. So here we've got 2 intersections there. So line CD is our secant. Okay, I think that's pretty good. Let's take a look at Example 2, draw an example of how two circles can intersect with no 1 and 2 points of intersection. Alright, so we'll do the first one for the no intersection first. So this one's no, and I mean, this simple little thing right here, right? We can just draw two circles that have no intersection. So circle A and circle B do not intersect. 2, 1 intersection. So if they have one intersection, what does that mean? They have to be what to each other? To be tangent, right? So I have circle C and circle D. They have, I'm saying they have one intersection here, intersect at point E. Let's say this is point E. And, you know, of course, if E is the point of tangency for circle C and D, if I were to draw a segment between, that's not a segment, if I were to draw a segment between CD, E would be on that segment. These would be collinear points. C, E, and D would be collinear. And then we would be able to draw a tangent through the point of tangency that would be perpendicular to that segment CD. Okay? So that's one intersection. And then the last one here, let's do it in eggplant. 3. We're going to have 2 points. And simply, we just draw two circles that intersect in two places, right? Just like that. So, F and G. So two intersections here. And, you know, from these intersections, we could draw a chord, or we could do a secant, or whatever. I'm going to note here on the one intersection, we could have also drawn this another way. Alternate way we could have done this. How about we get a different color here? So we could have done a circle inside a circle, and they have one intersection here. Right, they intersect at that point, H, let's say. And you know, we could draw a tangent through H, and it would be perpendicular to both of these radii here. I didn't draw that very well. Okay, but both these radii would be perpendicular to the tangent line that goes through the point of tangency H. Okay. Example 3, given the point of the center and a point on the circle, determine if the two circles are congruent. Okay. So I have two circles A and B. Looks like they intersect in two places. I want to know, we're given both the coordinates of these points, and we're given a coordinate of a point on each circle. Are they congruent? Okay, so if they're going to be congruent if both radii are congruent, right? Then the circles are congruent. Circle A would be congruent to circle B, something like that. So let's find, so we're going to use the distance formula here, right? Use distance formula. So the distance formula, well, I'm going to show you two ways, right? We could use the distance formula. So we do x2 minus x1 squared plus y2 minus y1 squared. So we're taking the difference of the x values, squaring them, and adding the difference of the y values, squaring them, and then we take the square root of that. And that gives us this. But I hope you see that this is just Pythagorean theorem, right? The distance formula is just the Pythagorean theorem written in a coordinate geometry. So really, this part right here is a squared. This part right here is b squared. We're adding them up together. And c is the hypotenuse, but we're taking the square root of it on the last step, right, of the Pythagorean theorem. So this really is just the Pythagorean theorem. So it might be easier to think of it in terms of Pythagorean theorem. It's up to you. So I think I will use Pythagorean theorem for, I'll do one for one and the other I'll do for b. So let's do the distance formula for a. So I'll just rewrite it. x2 minus x1 squared plus y2 minus y1 squared. So let's call a the first point. So this is x1, y1, and then x2, y2 is our point on circle A. So we got 0 minus negative 2. Okay, so x2 minus x1. 0 minus a negative 2. y2, 2 minus 1. And we have a double negative, so this becomes 2 squared plus 1 squared. We get 2 squared plus 1 squared is 5. The square root of 5. Okay, so that is our radius for circle A. It is root 5. So for B, I'm going to think in terms of Pythagorean theorem. We have a triangle here. And we've got a leg of 2, a leg of 2, and we want to find this hypotenuse, which we're calling C when we use Pythagorean theorem, but it's really the radius of circle B. Okay, so we've got a squared plus b squared equals c squared. So let's call this leg A, this leg B, and this leg R. That's our radius. So we've got 2 squared plus 2 squared equals r squared. 2 squared plus 2 squared, so that's 4 plus 4 is 8, equals r squared, and then we're going to take the square root both sides. And the square root of 8, well, the square root of 8 is 4, so 4 times 2 is 8, and then the square root of 4 is 2, so this is 2 root 2. So our radius here is 2 root 2. So root 5 and 2 root 2 are not equal. So the circles are not congruent. So circle A and circle B are not congruent. Yeah, and you know, we can see that by looking at them, right? I mean, we can see that circle B is larger than circle A, but you know, we can't just say because it looks. We have to say, we have to have evidence, provide reason, and there's our reason. We use the distance formula for one, Pythagorean theorem for the other. Okay, so example 4, I'm asking what is the distance between the circle centers. Okay, just kind of review again of what we were doing in our coordinate geometry last section. So we want to find segment AB, right? Find segment AB. And again, we could use the distance formula or we can use Pythagorean theorem. I'm going to use Pythagorean theorem this time. No, I won't. I'll use the distance formula. I don't feel like drawing on the figure. So we'll just use this again. We have x2 minus x1 squared, y2 minus y1 squared. Right, let's call A x1, y1, and B x2, y2, and we'll just substitute. So we get 2 minus negative 2 squared plus negative 1 is y2 minus 1 squared. 2 minus negative 2 is 4. 4 squared plus negative 2 squared. Oh, I'm running out of room. So let's bring it up here. D equals the square root of 16 plus 4 is 20. Okay, so now 20 simplifies. I'll just show you. If we do a factor tree, prime factorization tree for 20, on the left we're going to just take out our prime numbers, so 2 and 10 are factors of 20. Now we do 10. Right? What prime numbers are a factor of 10? 2 and 5. Now these are all prime numbers. So 2 times 2 times 5 is 20. Now we want to look out for any pairs. We have 2 2's right here. So really this means 2 squared, right, times 5 is 20. But what happens when we take the square root of something that's being squared? Cancels, doesn't it? Squaring and square rooting are inverse operations. So the 2 comes out and the 5 stays in, and this is the distance between the two circle centers, 2 root 5. Okay, last example here. I like this one. What is the equation of the line tangent between the given circles? Okay, so I've got two circles, circle A and circle C, and I see a point here. How can we make sure that this point is the point of tangency? So just call this point, how about I call this point B, maybe? I don't see, yeah, let's call this B. So this point is B. Is A, B, and C collinear? It's pretty important, because if they're not, it means that B is not going to be the point of tangency. So I'm going to draw a line segment from B to C, and it has to go through point B. It's pretty important that it does. I feel like my line's too thick now. Yeah, maybe a little bit bigger. So we could prove that these points are collinear by using distance formula and showing that AB plus BC equals AC. But we can also, for this problem, I think we can see that we have a certain rise over run here that we're getting. And we're rising 1 and running 2 along this segment. And the whole way we're intersecting through these points A, B, and C as we do that. So we can say that A, B, and C are collinear. So given that A, B, and C are collinear, B would be a point of tangency. So how do we get the tangent line? Well, AB is a radius, CB is a radius. The tangent is going to be perpendicular to both of these radii, right? Tangent line is going to be perpendicular. So how do we draw a perpendicular line, a line that goes through B that's perpendicular to this segment AC? So find a line perpendicular to AC that passes through point B. So what do we know about perpendicular lines? Perpendicular lines have two things: negative and reciprocal slopes. And what is a slope? The slope of a line is the amount that it rises or the amount that it runs, which is the change in y over the change in x, which is the difference in the y coordinates over the difference in the x coordinates. So let's find the slope of AC. We're going to find the slope of AC. So what we could do, if I do this algebraically, I know my point A is -4, 0, and my point C is 6, 5. This is, I can say x1, y1, and this is x2, y2. I can say y2, 5 minus 0, using this right here. 5 minus 0 over 6 minus -4, 6 minus -4 is 5 over 10, which is 1/2. Visually, we already determined that we are going up 1 over 2 the whole way here along this segment. So this is our slope for segment AC. Okay, so therefore, our slope perpendicular is going to be negative and reciprocal of this slope. So this is a positive number, we're going to make it negative, and we're going to switch the numerator and the denominator. That's what reciprocal means. So now we can go from our point B here, and we could count off our slope of -2 over 1. That gives us, zoom in on this. So we've got point down 2 over 1, down 2 over 1, down 2 over 1. Or we can go up 2 to the left 1, up 2 to the left 1. This point's important right there because that is where our line is going to intersect our y-axis, and we call that the y-intercept, which we use to write an equation of a line. So our y-intercept, we use little b, is 7, and we already determined our slope is -2 over 1. So our equation for this line is going to be the equation is y. We're going to put this in y equals mx plus b form. Let me just write it. Y equals negative 2x plus 7. Now we just wrote this in y equals mx plus b form. This is our slope-intercept form right there. Okay, there we are. So that is the equation of the tangent line that passes through circles A and C. And the point of tangency has to be linear with A and C. Otherwise, it wouldn't be the point of tangency. Okay, very good. We covered a lot in this section. You have a practice set that we will work on next. All right, everybody. I'll see you.